Welcome to Topic 6, Unit 2, Finding Limits, Properties of Limits. So in the last lesson we looked at what limits are and we examined how to find them both graphically and by using a table. In order for us to use different strategies to find limits, we have to look at the properties of limits. So I'm going to run through these properties pretty quickly just so you know that they exist, because they're going to allow us to use the strategies that we're going to take a little more time going over in this video. So the first property that I want you to see is the limit of a constant. And the limit of a constant, the limit as x approaches c of f of x, is just equal to whatever the constant is, which is b. So if we look at this graph right here, this is the constant function f of x is equal to b. It doesn't matter what x value you have, no matter what, the graph is always approaching b. The second limit we're going to look at is the limit of x, which is the identity function f of x is equal to x. And it says here that the limit as x approaches c of x is just going to be equal to whatever x value you plug in. So this is simply equal to c. So you can see that if I plug in the value c, my output, or the y value I'm approaching, is also going to be equal to c. So if we break down the properties of limits, we're just going to work with the idea that if we have the limit as x approaches c of f of x, if that's equal to the number L, and the limit as x approaches c of g of x is equal to the number m, we have a sum rule that says if you're adding two functions inside of a limit, you can just add their limits. We have a difference rule that says if you're subtracting two functions inside of a limit, you can subtract their limits. A product rule says multiplying is the same as multiplying their limits. The constant multiple rule says that if you're taking the limit of a constant times a function, you can just take the constant and multiply it times the limit. We have a quotient rule that says that if we're taking the limit of a quotient, this can be equal to the quotient of their limits, provided that m does not equal 0. And then we have our power rule that says if we take the limit of a function raised to some power, even a rational exponent, it's just going to be the limit raised to that exponent. So now we're going to look at a list of techniques for finding limits. The first two things on the list are what we used in the last lesson. We can look at the graph of a function to figure out its limit, or we can make a table of x values that get progressively closer to our c from the left and from the right. But now we're going to look at other things that we can do. So technique 3, substitute c in for x. So whenever possible, if I can just plug in my c value into the function inside the limit and get a number, that's the value of the limit. So this is going to be equal to 4 times 2 minus 3, or 8 minus 3, which is equal to 5. Another technique is to factor, divide, then substitute. This is something that happens when you have the limit of a quotient, and if you try to plug in the c value and you wind up dividing by 0. In this case, if I plug in the 1, I'm going to divide by 0. But if you remember in the last lesson that just because you have a hole in a graph does not mean the limit doesn't exist. So if I were to factor and divide and cancel out the factor in the denominator that is causing me to divide by 0, that just means there's a hole in the graph and I can still find the limit. So let's try this. The numerator is the difference of cubes. So I'll factor that into x minus 1 times x squared plus x plus 1 all over x minus 1. The x minus 1 factors cancel, which means there is a hole at x equals 1, but that's okay, because now I can plug in my 1 and I wind up getting that the value of this limit is equal to 3. And then our fifth technique is if the function has two different values, substitute into the one where x doesn't equal c. Again, this was something we saw in the last lesson. When you have a piecewise function that is defined for one x value and then for every other x value, that basically means that you have some point defined, and then you have another function that has a hole right where the point was defined. And when you look at this, it's the value at the hole that is equal to the limit, not the value of the function. So when we look at what we were given, we want to look at how this is defined for everything except x equals 7 if we want to evaluate the limit at 7. So that means I'm going to plug in, so my limit as x approaches 7 of k of x is going to be equal to 7 plus 3, which is equal to 10. Example 1, find the limit as x approaches negative 3 of x plus 4. If you can plug in the c, then do it. So negative 3 plus 4 is equal to 1. Example 2, the limit as x approaches negative 5 of negative 4x. I can plug in the negative 5, so I've got negative 4 times negative 5, which equals 20. Example 3, find the limit as x approaches 2 of 5x squared. I'm going to plug in my 2, and 5 times 4 is equal to 20. Example 4, we're going to find the limit of that polynomial, and we are free to just plug in the 2. So this is equal to 5 times 2 to the 4th minus 6 times 2 cubed plus 3 times 2 squared plus 4 times 2 minus 2. And this is equal to 80 minus 48 plus 12 plus 8 minus 2, which all combines together to equal 50. Example 5, we're going to explore a few different functions that are raised to powers. For part A, I can plug in the 1, so I'm going to do that. So I've got 3 times 1 minus 5 to the 4th, and 3 minus 5 is negative 2, and negative 2 to the 4th is positive 16. Part B, the limit as x approaches 0 of the square root of 5x squared plus 8. As long as I'm not undefined, when I plug in that 0, I'm okay. So let's see what happens. Undefined would mean I'm taking the square root of a negative number. So I've got 5 times 0 squared plus 8, which is the square root of 8, which is a real number, and I'll simplify that to 2 times the square root of 2. And then we have part C. We're raising to a rational exponent. So I'm going to go ahead and plug in my negative 1. So this is going to be the same as 5 times negative 1 cubed minus negative 1 plus 3 to the 4 thirds. This simplifies to negative 5. This simplifies to plus 1 plus 3 to the 4 thirds. And negative 5 plus 4 is equal to negative 1 to the 4 thirds. But that's okay. It is all right for us to take the cube root of a negative number. The cube root of negative 1 is still negative 1 raised to the 4th, but when I raise a negative to an even power, I wind up with a positive 1. When we see rational functions, we have to be careful that we're not dividing by 0. So for example 6, if we were to plug in a 1 into this function, I would get 3 plus 4 equals 7 in the denominator, which means it's defined at x equals 1, so I don't need to try to factor and cancel. I'm just going to go ahead and plug in my 1. And the numerator becomes 5 minus 1 plus 2, which is equal to 6. And my denominator is 3 plus 4, which is equal to 7. Example 7, however, if I plug in a 3 into that denominator, I'm going to be dividing by 0. So I need to see if I can factor and cancel. So remember that until I can plug in the x equals 3 into the equation, this is still a limit, so you have to call it a limit. Now I'm going to factor the denominator first because that one's easy. It's the difference of squares. So that's x plus 3 times x minus 3. And then when I look at the numerator, I ask what are the factors of negative 6 that add up to negative 1? And that is positive 2 and negative 3. So this is x plus 2 over x minus 3. And fortunately for us, the x minus 3's cancel, which means there's a hole at x equals 3. So we can find the limit by now just plugging in 3 plus 2 over 3 plus 3, or 5/6. Example 8 is another rational function, and if you look at it quickly at the denominator, 2 to the 4th is 16, and negative 2 times x cubed is negative 16. Basically, if I plug in a 2, I'm going to be dividing by 0, so I'm going to have to factor and cancel again. So because I have 4 terms in the numerator and in the denominator, I'm going to factor by grouping. So in the numerator on the left, I can take out a GCF of x squared, and I'm left with x minus 2. And on the right, I can take out a GCF of 4, and I'm left with an x minus 2. On the left side of the denominator, my GCF is x cubed, and I leave behind an x minus 2. And on the right, I just have x minus 2, but I'm just going to write it as if I factored out a 1 from x minus 2. So I can actually factor out an x minus 2 from both the numerator and the denominator, and it's going to look like this in factored form. So I've got x squared plus 4 times x minus 2 over x cubed plus 1 times x minus 2. So the x minus 2 factors cancel, which means we have a whole at x equals 2. Now I can find the limit by plugging in 2 into what was left. So I have 2 squared plus 4 over 2 cubed plus 1, or 4 plus 4 is 8, and 8 plus 1 is equal to 9. Example 9. Find the average rate of change of f of x plus h minus f of x over h for f of x equals x squared minus 2. So what they want us to do is substitute in f of x plus h and f of x into this expression right here. So remember, if you were going to find f of 1, you would plug in a 1 for x. If we're going to find f of x plus h, we're going to substitute in x plus h in for x in our equation. So this becomes x plus h squared minus 2 minus, now I'll just substitute in f of x, which is x squared minus 2 all over h. The next step would be to simplify the numerator, so I will simplify x plus h squared by foiling. I get x squared plus 2xh plus h squared minus 2. I'll distribute the negative and I get negative x squared plus 2 whole thing over h. Now things can cancel in the numerator. I have a positive x squared and a negative x squared, a negative 2 and a positive 2, and now I'm just left with two terms in the numerator that each are divisible by h. So I will take 2xh over h and simplify that to 2x, and I will take h squared over h and turn that into h. That's all for now. Thanks for watching.